Okay, good morning and welcome to lecture 8 today. Thank you so much for enduring with me this week online. I hope next week I will be able to commute regularly to school. Before we start with the lecture, I want to comment on the homework, the assignment for next week, right, which was announced on Sunday. So I will share the screen one moment to see. So we had two choices. You have to choose one of them, right? One is, this one is in the screen. I chose, just to have some kind of interesting criteria, two buildings of just 100 years ago, which sounds cool. One is a Citroen house, right? By Le Corbusier. There are several versions, and we are proposing the one we have on the screen, right? The one on Pilotti. This is a simple, like early skeleton structure. It is not built, so it is very good opportunity to find out how the structure is and to exercise a little bit on drawing a structure diagram in plan and section, okay? You don't need to draw walls and things like that and windows, because we need to know just the columns, the slabs. Go to the lecture, right? And it is worth to listen again. Lecture, right, on drawing of structures, and also the if you go to Blackboard assignments, you have our activities and assignments. I think you have our reference materials, you have a assignments checklist, right? So look at it, general points and the ones related to structure. So see the checklist before you do anything, right? So one possibility is Citroen house. I suggested one A3 at least, and to work at the audio is not good. Let me see if that works. Thank you for telling. I have the microphone on and here, so should be okay. Is everybody having problems with audio? Okay, maybe I should talk a bit louder. Okay, thank you. Probably it was a network problem, because I'm broadcasting from home, and probably network is not great, okay? School is not great either, but okay. So I suggested 1A3 for whatever case, and for this building, if you have to make several floor plans and one section, probably 1 to 200 is okay. 1 to 100 is better, but you have to check, because we're working in diagram level, so we don't need to detail a lot, right? So this is one thing. The other alternative is another project for 1922, right? And this is the glass tower, not the first one. This was 1 year earlier. This is already 101 years old, right? The one in glass, which I think still is quite unique and quite fresh design. In this case, it's a full tower. So I wish you concentrate in just giving the diagram for one floor plan, right, to see how that works. And section, just a set of like at least the 3 floors, right? So you have the idea on how they relate, right? And in this case, this building is huge. So probably 1 to 200 is too big. You might go to 1 to 300, which is not great scale, or a bit smaller. So you can really fit there, right? Optionally, you might go to foundations and the bracing of the full structure if you want. It's not necessary. The information I provide is an interesting article. I put the whole article because it discusses about possibilities of a structure, right? So this is just a hypothesis. They call it here the mushroom, right? This is for concrete, right? For steel, if you remember, we spoke of the umbrella, which is not official term, right? But and you may have any other kind of structure. This is quite difficult to materialize. And Mies van der Rohe himself tried something and didn't find any solution for this specific project. You can experiment with whichever you find more suitable for this, okay? So again, I think next week is time enough, right? And again, you should spend probably a couple of hours, maybe a bit more if you want to do some research. And if you want more information on this article, this project is very published. You can go to the MoMA, right? New York MoMA homepage, and you will find a lot of the original drawings of this project and many projects of Mies van der Rohe and many other people, but there are many more sources. Okay, so much for the assignment. If you have doubts, please ask, okay? But again, I insist, the assignment checklist is there to help. Read it before you do the assignment. And we have some chapters in the structural systems lectures about how to draw, how to think, how to diagram structures. So look at them also. It's kind of exercise of thinking structures, but also expressing them, right? Good. Now let's go into the lecture because we have to work fast. Okay, let's start. Let's go to Keynote and start. Oh, the photo moved unwillingly. So we'll start with the envelopes, and I will try to not repeat too much from materials. Also, many of you may already forget. So I will try today to see the basics, which is exactly the same we saw in materials, almost. Maybe a bit more detail, and then we'll try to concentrate on the first part of the envelope, which is the plinth, the connection with the ground. In the photo, it is a famous Samsung building in Gangnam, right? One of the cool, expensive, and good quality curtain walls we can see in Seoul. So we will try to go to the introduction, basics, and then spend some time with the plinth. Let's see how far we can go without rushing. Still, some of you find it difficult to follow the English, right? And also my scribble, my handwriting. It's hard to write with this while you talk. I'm not a multitasking guy. If I write, I write. If I speak, I speak. But fortunately, all lectures are in YouTube. So I think listening back and slowing down and repeating the areas which are more difficult might help. I mean, how I try really not to rush, but sometimes my mind is much faster than my own talk and my own will. In order not to repeat too much, since this is mostly what we saw already, and it's not worth repeating with detail, I just give you the link to the lecture of last year. It's about 30 minutes, in which you can go back and you can see all the detail of what we'll see here very fast. So we can just go fast into the details, right? Which is, I think, more interesting now. So remember, we have been speaking about the skeleton and its essential function. It is the load support of the building, right? It's quite nice. Interesting, you see this is a full slab only, no beams, even not, well, capitals are embedded in the thickness. We'll see this project later. It's not mine, I just happened to see this this summer. Also, this photo is from a couple of months ago. But you can have a perfect structure without too much thickness, right? And see that the spans are reasonably regular. There's a few narrow ones. See how usually the narrow ones are in the corners, not always, but well, this is quite reasonable structure for housing. But we need more, right? So the envelope is what really creates the interior space that regulates the interior environment. So it will control how much water, so we'll protect from water. That's mostly the roof and the facade. will also protect us and regulate the light and the heat, will take the air out, regulate how much ventilation we need, will protect us from noise, and last from intruders, right? So it's 5 very clear functions which sometimes are in conflict. This is the summary. So this is what we have about the environment, right? As we commented in the slide before, and the safety. But it has also structural role, and it is mostly the image. So it has to do a lot with design. And this is what we call it. It's just one day in Archdaily telling how much facade is where we put effort to have some uniqueness. So how can we combine all those functions in our design work? Because only one will not be enough. So remember, this is a review, right? Construction design is just choosing materials and dimensions, because materials are not endless. It's an important point. Then, since materials are finite in size, we need to see how we make the joints. And then once we do, it's just how we join systems, right? Like a structure and envelope, a facade and roof, a facade and ground, and so on. So this, if you see, detailing is spending our life thinking how to solve joints and then expressing them in the drawings and then experimenting and checking that on site. This is borrowed from materials. In the case of brick, it's very clear, brick sizes, and you see this kind of a lot of different standards, but mostly related to what we can hold with hand. Then there's the putting them together. In the case of brick, it's very clear. There's a lot of experience. It's what we call the bond, right? And then finally, how we put this bonded brick relation with the structure, right? So in this case, you have some kind of a structural element. We will have the brick hanging from the slab. So let's go into some basics, right, on what we have to take into account. First is the construction. Tectonic is about how we make things materially, right? How put things together. And well, we have the old dichotomy between tectonics and stereotomy, and then relations with structure, and then the multi-layering. It's like the most 3 basic decisions we take in a project. First, tectonics versus stereotomy. Remember that stereotomy refers to heavy, massive construction, and I chose Mies van der Rohe just to celebrate his 100 years of the glass tower, in which, even though this is a modern building, clearly the mass is as important as the space, right? This is like a massive construction. By contrast, again, Mies van der Rohe, to system architect, roof work, tectonics, filigree refers to assembly, right? To light construction, like a skeleton, right? So with the same materials, just brick and glass, we have totally different construction problem, and of course, design problem. Then how structure and envelope relate. There's 2 choices, envelope and structure are coincidental. This is very common even in modern architecture, or they can be separated, as is the case of the modern curtain wall. And we have plenty of in-between cases. So remember, we saw some kind of possibilities on how envelope and vertical structure, that means columns mostly, relate. We had like 3 basic possibilities, right? So depending of the envelope wrapping the structure or the structure getting on the outside, this is what we call exoskeleton, right? Right. We have more protection on the envelope or more protection on the structure, and more difficult to make skeleton or envelope, and easier, more protected to make envelope, right? And this is quite practical, but has other issues. If we see this in plan, you can understand the exoskeleton has the big problem of thermal breaches, right? And water coming in those joints. This is quite difficult to solve. Very practical system, as the case of Mies van der Rohe we saw before. It is very practical, very original, but you have a terrible, difficult joints to solve. And then one of the most common, right, in which you have columns inside, which many people might hate, but you have still the envelope outside. So these 3 examples, right, of the envelope really wrapping the structure, being in contact. This is Miss van der Rohe, one of the few reinforced concrete towers he did, and the famous Urban Hive tower, which is a case of an exoskeleton. If we consider only the horizontal structure, that means the slabs, right? We can also think independent of the columns. We may have what we call the curtain wall, which is just hanging, right? Clearly with an intermediate element attached to the slab. Can be tangent. This is what some people call the false curtain wall. And then partial support and totally inside, which is also 4 different options. This is a very clear case, right, during construction, in which we see really the curtain wall element is clearly separated from the slab, from the structure. There's some element in between supporting it. This is a case of bricks, right, in which, as we saw in the example before, one structural element connects to the slab. So we have a continuous insulation. Of course, we cannot avoid a very tiny thermal breach there. And tangent has several possibilities, right? One very much used with light prefabrication, one very much used with masonry and other materials. This is very, you can see many places in Seoul. The most common for prefabrication, and then one variation of the sample also before, but it doesn't allow for continuity of insulation, right? This is a bit more safe, easier, but has this difficulty. So what we see is that 2 of them are very strong in thermal breaches, while the other 2 allow for a very regular continuity of the envelope on the structure. One thing you have to be careful when you work with the masonry especially is to support at least 2/3 of the masonry, right? So the gravity center is well supported, it will not fall, or to have an structural element, and always leave a gap, because the slabs have always some deflection. We know by structural studies that it will move, and usually this is getting a lot of weight. So when you have the slab, we put in the bricks, right? We put the following floor bricks, the 2/3, right? And we leave a small gap. And we wait a few weeks, right, until we really complete this area. So we wait for the slab just to settle the few millimeters, it will settle. So when we put a mortar, it will not crash the brick. Sometimes they use some kind of elastic material, not really mortar, right? On the outside, you will have mortar always. So this is the point here, which is very common in masonry construction. Okay, and this is how you draw in a real detail, right? This is an example on how this works in real life. And this is what happens when you don't have that proper support. Facades fall down, right? So disasters are not very common, but they happen more than we want to build. Especially rain softens a little bit, the material makes it heavier. When you have heavy wind, probably things have a disaster. Something which became common in modern architecture is the multi-layered envelope versus the single layer, which is probably traditional. But we have, as we saw, materials, modern elements which work very well in temperate climates when you don't have a huge needs for insulation. And we are recovering traditional systems like rammed earth, in which we can really make buildings quite interestingly in modern sense. See this detail, which is interesting. See how when you have those elements which are structural, right? This is structural. But the columns, the concrete will help this to have more rigidity, right? More stability. There is always a gap, right? Usually masonry and concrete and steel even less do not touch. And you have one connection every few meters, which gives stability. So that is a support point, but this is flexible, right? It will move. So the few millimeters of differential movement, the even settlement or wind or just the expansion will be absorbed by this plate, which is thin, it's elastic, and it will not have cracks, will not force the weakest element with the masonry to crack. Interesting thing, and this is a usual exam question. Okay, curiously, curtain walls conceptually are single layer, in general, even though we have multi-layer glass, but this is like a really conceptually one element only, right? So for multi-layer, we have many, but most essential is the load bearing. This is a structural part. Insulation is basic in many places, and the exterior protection or finish, right? So this is the most common layers we have. We have, of course, additional finish and shadings, and they can be swapped in position, right? And some of them can be coincidental, right? They may happen, but you will see in the book, at least the textbook, they will have the symbols like protection, load bearing, and insulation layer, which is the most basics. We commented you have plenty of documentation on these series of multi-layered walls, right? And you have buildingscience.com. They have a huge collection in which you will try to refine to have the perfect solution. I think they go too far, but really, if you want to be going near to the zero energy or the passive house, you will need really to work even the tiniest details. We have, of course, multi-layered curtain walls, very expensive, very complex, but they add this kind of shading layer and the filtering, light filtering, so this is the protection, right? And then finally the glass. So you have to add devices to make those curtain walls a bit more useful, because the problem with curtain walls is that we are totally unprotected against sunshine and privacy, right? And in some climates, at some times of the year, in some orientations, this is a big problem. I add the trombe wall is a 140-year-old invention. This is the patent, right? And it consists on a glass element which allows the sunshine to go through and heat one heavy element. So depending on how you let the air in and be preheated, or at night heat the air with this kind of element, or have the ventilation when it is very hot, right, and the air cool down. It is very ingenious and very useful system. Just by curiosity, this Morse is different from Edward Morse, from the Morse code inventor. He was a biologist, a zoologist, but he wrote one of the most famous books on Japanese houses with great drawings, which is embarrassing that a zoologist makes a better book on architecture than architects. For the multi-layer, there is something that you surely studied in other courses, but we have to repeat. Since we have a strong insulation layer, we have a big temperature difference, right, between interior and exterior. You might have points where you condense water, where the vapor inside gets cool enough to wet the insulation of the inner walls, and that's a problem. We have two strategies to ventilate. So this is the open joint ventilated chamber, which will dry this kind of condensation, and it works well. And the vapor barrier, which will let the vapor in the hot side, right, in this case, so it will never condensate. You can combine both, of course, right? But it's worth you're aware of this. But in most cases, you will have to calculate, or somebody will have to calculate for you. So let's have, even though we said we will go fast, let us have one question. I hope you downloaded. The sheet was in Blackboard. Let me know if you have some difficulty. I'll just spend just a couple of minutes to see this. This is very easy. So condensation may happen differently in winter and in summer, right? We know, we can think on solar climate. We have very dry climate on the outside, but it can be a lot of humidity in the interior. On summer, we have a lot of humidity outside, inside might be very dry, right? This is a huge temperature difference. And then if we have condensation in the interior, which things we should do? Please mark wrong or correct. And we have 1 more minute left. remember, you can do by hand on computer. You have to upload this before noon in the link I think you have in Blackboard also. And this was exam question. And actually, it's exam question in materials and also in building systems. Since some people have problem translating condensation, I try to put in the Google translation of all. You can just correct if some of them is not right, because I know we have Russian speakers here. Okay, let's continue. So climate and environment is essential, and it is surprising many envelopes are designed forgetting totally about this, right? And we have to be very aware of the local climate, right? Sun and wind, and we compared a very well organized architecture, right, which we know very well, and totally not architecture which has no into account any kind of sunshine or wind, whatever. It relies 100% on mechanical systems, right? So I would question if this is the right way of doing. And regarding the climate, increasing or reducing thermal mass is one tool we have, and then letting sunshine and reducing wind, or the opposite, hiding sunshine and letting air in, are strategies which are pure design strategies which may improve enormously the performance. This is the graph of the thermal mass. I will not explain it, you have in the video, and it's an example in which heavy thermal mass has a very good effect in climates. And this is one case of a natural ventilation, which is traditional and it's kind of disappeared in modern construction, right? The most modern we have, the less ventilation we may have, which I have difficulty to understand why. Finally, one word on protection. Envelope protects us against intruders. We have this kind of privacy problem. This is a movie trying to make a kind of a parody of that all glass buildings in which you have no privacy at all. Even at the street level, you're like a show window, right? So privacy is one thing we have to consider. We don't like people to look at us when we are in our private life. And let me see if we can continue. And then we have the problem with anti-theft. The more safety the society is, the less we need. But yet we all feel a need to have protection. One thing I want to comment is that there is incompatibility between anti-intruders and the safety, right? If you don't let people get in, you cannot get out. And in case of emergency and fire, this is a problem. And we have many casualties, people dying, and this is one floor house. But those guys, they have time to go to the door and escape. And firemen could not help because it takes time to remove this kind of a barrier. So my advice is never do that in projects, right? Safety is first. If people want to make their own protection in the windows, they can do themselves. If there is a casualty there because you put some barrier which prevented people from escaping, you might be responsible for it. So I try to avoid it. So let's go fast into the design process outline. We need always to know how much we need to work with the climate and how we'll deal with the interior environment, especially in terms of light, air, and noise, right? Ventilation. Fortunately, we can have simulations for sunshine. We have plenty of information in the web, and we have free access to simulation tools. Surely you used already in other courses, I will not insist. NREL is the one we use worldwide. We can complain of the United States, but this is one thing. They create a very complex, very useful tool that's totally open to use everywhere, right? They are, I'm not sure they are still there because I didn't check, but you have like a online free software to simulate natural light, which is quite interesting. Before we had just to guess ourselves. So once we have those studies and we know how much it will work, we have to start from the usually from the section, right? We have to identify the difficult points, which is usually plinth, the typical walls, and the connections with the roof, right? These are like 3 points or 4 points we need to work always. This is like a ground level. So we have to decide about all those issues we considered before. And then we have to combine that with our design intentions and the possibilities of the site, the context, the material we have at hand, and so, right? So it's many things we have to choose, right? So you have this kind of summary of this we're commenting, right? Then we have some context. So you have your design concept, of course. And in school, we seldom go beyond this point, but you'd have economical limitations, and also have to think on the future, right? How this will be maintained, can be reused, or how it deals with the sustainability. The material schedule is something we did in materials, and also helps for choosing those materials along the design process, right? And then, as we said, we have to define, so we choose the materials, we define the dimensions. This is an example of a good facade in which the dimension of the cladding system is very well chosen. And then we have to solve the joints, right? The illustrations are all students' projects. And then joints between systems and subsystems, right? Roof facade, facade ground, envelope, construction, right? And well, this is something we insisted in structures, and it happens in general. When we detail, we have to think the real construction project, right? There's people really put in those elements, and we have to visualize and to think how they can do it really. And then we have the envelope project, which is kind of sub-project in the general project. So you have to complete the details to complete the full definition of materials. Again, school works ends here, right? But you have to make a cost estimation, integrate in the project, and then sample boards and so on. This is students' designs. This is an example of material table or schedule in a simple project. We'll comment on that in the interior lecture. And this is an example of the published statistics of cost of construction, which helps. This is published in every country in their own way. So you would have an estimation of how much your building might cost related to what people are building in the same kind of typology. And then you end with the drawings and texts, right? And this makes the project. Then models, renders are support materials, and as much as possible, as we said in construction management, I would advise to let them out of the contract, because those documents are less reliable, and you may have things in the renders or the models which are adjusted later, and that might create problems with your clients. So you have to make always very clear, if possible, then these are not contract documents. Material samples is interesting because we need to see the things that come really to the construction site, see them by side, and so on. So it helps taking decisions. And then we have what we saw very fast outlined. This is kind of a very basic checklist of how we should proceed when dealing with the envelope at design level. This is not exam question. You don't need to memorize, but I think it's interesting you are aware of this. So this is a very short question, right? And this is like 30 seconds. Just say yes or not. Did you remember everything we commented now? Or you think you need to go back to the video and see it slowly and review it again because it's worth just say yes or not. 30 seconds, still 15 left. So we can continue with the interesting part, which is detailing of the plinth. Okay, let's continue. So, you know, plinth is called in many ways, basically it's the connection of the building and the ground. This is one of the critical parts, and one which traditionally has a lot of effort. And curiously, in school works, in modern works, it's not always dealt with the care it needs. In the textbook, the Places, we have almost all possibilities. See that they work always with the small buildings, right? So this is not a book for skyscrapers, and we have only one basement. This is one limitation of the book. but it is very systematic. As a good Swiss handbook, German-based, they're very systematic, right? So the most common is just the plinth, right? Just the intermediate element for one floor building. It's a typical platform of classical buildings or in Europe or in Asia, right? So basically, they help to protect against humidity, and we have this is something we understood very recently: radon gas. Of course, the most basic is to level, right, the ground. So we have irregular ground, so that helps to have horizontal, perfectly flat, where we can carry our life, right? But there are two functions, which are humidity and radon gas, apart from that leveling. Against humidity, they are the most basic. This is real construction. You may have a gravel layer, which allows the water just to filter. So under the slab, you can gravel, right? So the water will not go up. You may have like a waterproof layer under also, or you may have this kind of, there's plenty of patents, kind of raised form, right? So you have the ground, you have some kind of raised form where you will put your concrete and will let the air ventilate through, right? There's many ways of doing it. You can also raise the floor. So this is the case of a plinth, and you have one space just enough for people just to crawl inside and to check the systems, right? This could be a detail of much smaller. Usually we put at least 30 centimeters and we'll let some openings for the air to move in. Not too much, otherwise you have a lot of energy loss, but enough for that humidity to evaporate and to get out, right? And you see that there is some element here. They put a bit high, so this is not my detail. I remember, but usually you will have this kind of waterproofing element, which I would put in this point, right, as they do here, right? You'll see this is prefabricated ribs with a lost form. So in this case, the concrete will be poured over, right, to complete the structure. And you see this kind of element to cut the humidity which may come in this lower part. And of course, this area has ventilation. This is how this is done. This is just a reminder to see how it works. So this is the prefabricated ribs, the metal mesh, right? And this is like a side beams just to complete, right, the strength of the slab. So if we make the section, we'll have a one beam, prefabricated rib, the form, another rib, right? And then concrete will be filling inside. And then those elements in the border have their own reinforcement, and they will help to have a very well-tied element. Even if we make only masonry walls, this is the case, it is good to have always one beam tying all the border, right? And this is what we show here. This is example. So for radon, we understood, we knew about this like 25 years ago, right? So I didn't study this at school, but it is very cancer causing. And this is a gas which comes from the underground, especially in usually from uranium decomposition. And this comes from granite, usually. Not always, so it's more sounds, but granite is very common, and it may have remains of uranium decomposition, which will create radon. So if you have a basement in contact with the ground, you may have this kind of poisonous gas, right, going in. And this kind of a basement or half basement floors are very common everywhere in the world, and also here in Seoul. And Seoul, Korea, especially Seoul, is very much granite place, right? So to avoid this, it's very easy to have this kind of ventilation, the same way used for humidity, but make sure that gas is ventilated and goes out. Or you can make a chimney just dissipating through the roof, which is even much better, right? And then it's not dangerous. After a few years, this dissipates, it's not dangerous anymore, but that's something we have to be careful. We have published the radon maps. You see, we have some areas of Spain which are really, really strong on that. Some areas in Finland, for example, it's map of the states, and surely you have some map of radon estimation in Seoul. But this is one of the data you should get from the geological survey. Next is having this kind of ground floor, not just the small element for ventilation or for accessing the systems, right? The drainage pipes and so on, but to have like a full floor which gives more separation. And this is very common. It will happen, well, this is one of the nice examples, famous one, in which just a plinth becomes a full floor, right? But helps leveling the house in a place which is a mountain. You see, if this was done in Korea, and we have this kind of hill, we would call the civil engineer, and they will flatten the land with a retention wall, and they will put the land flat, and then we would make our house on top. And this is by law. I don't know why, but in Korea, Riskan would have been unable to make Fisher house as he did. I wish something changed in the way we do things here in Korea, because probably this is much more gentle way of dealing with the landscape than just breaking all mountains before we even think how to build over them. Well, this is the point we're studying, right? The connection of the ground. This is one rare photo of the construction. This is like a really rough rubble stone construction, which leaves this kind of a flat horizontal element from which to start the real house. This is big enough to have an extra floor, which is usually used for storage, secondary spaces, right? This is the same case. This is in Tokyo, which have the huge elements in which the foundation, the plinth is just elastic elements, just for earthquake absorption, right? And this is usually a combination of neoprene discs with the steel disc in between. You see the division. So you have a very strong element with smaller elements. This is to avoid to have too much expansion of one single element. So you have more redundancy. And you see this is a full building just supported by this kind of 4-point, right? This is normally strong. But this is enough to have the building stable under a big shake. Well, I told neoprene, I think it's neoprene, but could be much more sophisticated polymer. I don't know exactly what they used. So this is probably neoprene, right? Then we have what we are more interested in, the one with the basements, the more difficult, and could be like a half basement in which you have some ventilation. This is extremely common and useful, or just a totally hidden basement. This is one example of a housing where actually people were living in those spaces, right? You see the granite, again, to be more strong structurally, but also to have more strength against the water capillarity rather than the brick, right? And then probably the ones we see most often, which is what we call the sunken, right? For which we have kind of love affair here in Korea. And we said, well, one of the most beautiful sunken I see is the Fukutake Hall by Tadao and the Tokyo University, in which the building is only 2 floors over the ground and then 2 floors underground. So it avoids to be too tall and kind of respects the landscape of you still have ventilation, natural light, and a nice space in those kind of meeting auditoriums in the basement. So let's go into the details. So we did first, and actually we have just 30 minutes left. Hope it is okay, but this is where we have more material, more details, and more variations than we had in materials. So let's go again through the basic. Again, most of the details are taken from the textbook of the classes, right? But that book is just for small buildings, small basements, usually 1 floor, maybe 2 floors at most, right? Many of you have huge buildings, huge facilities, skyscrapers, and this kind of detail does not apply at all. Again, we have a lot of possibilities from the half basement to the level floor to just a pilotis. And we have the examples with the insulation out or the insulation in, right? We will go to the most complex, which is the half basement. This is the case we have in the Fisher house, and I brought a detail. This is not, I don't have better detail than this, but it's interesting to see many things that we have to pay attention. First is the separation of the ground to the sensitive material, which is timber, right? And usually it's about, sorry, about 30 centimeters or more, right? Then we have this small little bit. You see that if we enlarge this tail, we have the rubble stone material, right? And we have the timber, which is slightly away from that wall and has a small little bit. This allows the water to slide and to drip, right? So I call a dripper or drip, right? So the water does not go to the joints, which is the critical point, right? This is an important thing. Then you have another element, which is the waterproof element between stone and timber. So all possible humidity which comes by capillarity, right, from the stone will stop in this point and will not affect the timber. So there are three things, right, that are basic in any kind of connection with the ground. And in this case, the sensitive material is the timber. This is the title from the book, the one we did in materials, and this is the most generic. And again, you will see that we have, again, this separation, the drip element, right? The waterproof part, right? And then we have more, which are interesting. So we have like already 3 points to take care about. Then we have number 4, which is this gravel, right? Which helps to drain, but also to diffuse water. So when the rain falls over the gravel, the drops are smashed into small spray, and they will not be so aggressive to the wall, right? Then 5 is this layer, which is a drainage layer, right? So the water happens in the ground, and instead of pushing and making pressure to the wall, it has an empty void from which it falls and is collected, right? Of course, we will usually have a waterproof, waterproof layer. And then going down, we have number 7, which is a kind of felt, right? Or filter. So the water again is going down, but you have water and you have a lot of sand, fine elements. So to make sure things do not get clogged, only the water goes on, we have this kind of filter, right? There. Then we have again number 8, which is a gravel. Let's go back to here. Okay, 8, which is gravel, right? Which is making easier the water just to go faster to the final point, which is 9, which is the drainage pipe, right? Which is a pipe which is usually perforated or porous, so the water will naturally go in and then go out. And this pipe will have probably about 1% of slope. So the water just goes to the collection area, right? So you'll have to think that this element here will need some kind of a height margin, so you can go down until you have the exit, right? So we have like 9 elements, which are the basics of most basements. Then you can have variations. This can be brick, concrete, mortar wall. You may have the insulation outside, inside. This can be, again, timber, as we saw before. Things can change, but all those things are what we have. And see that the area I circle in blue is the part we see. And this is most difficult. Just walk around in Seoul and see the buildings and see how this connection of the building with the ground is always difficult, sometimes terrible, sometimes elegant, sometimes dirty, but always difficult. This is a good exam question. So we have 2 delicate points, right? So I have one more question for you to think. This is question 3. This is actually, just forget about those boxes. They have no relation, and forget the pipe. But it's a clear problem in this wall. And the question is, what did the architect miss? The detail actually did is miss, right? So it's redundancy there. You can write or you can sketch clearly the section. We reviewed all the elements. This is clearly the ground, right? And this is nice, very expensive white brick with a cement mortar, right? And this is the 1 floor height, more or less. And something happens. I think you need only 1 minute to reply to this because this is quite easy. This was exam question 2013, I think. This is famous Honky Museum, which is a beautiful building by a good architect, but has issues. And actually, water leaks was always one issue from the beginning. But it's not leak from the roof. I want to see your opinions. Okay, a few more seconds because we have a lot of variation details to see and comment. Well, actually, it's only like 40 slides left. 3 slides per minute, so you have to rush. Okay, I think enough for question 3. This is an example of historical wall, right? This is University of Tokyo. It's probably 18th century. And you can see the asphalt layer, right? You see the foundation, the asphalt, and the first floor. So this kind of a space between foundation and the rest of the structure, right? This is a remain. This is kind of historical archaeological rest, but it's quite interesting to see how those precautions have been always taken into account in the construction. This is a variation. So we can see that there is a difference. Let me see if I put an annotation at the top. So I think, in my opinion, I would put the drip element. I think this is a danger. So you will have a filtering joint, right? You have splashes. So this is also something we see often, but that will be more unprotected. So this element will work worse. But we have an open joint, right? So open joints everywhere, so the water will filter, and we have still the gravel, the drainage wall, and so on. Here, instead of that felt, we have a drainage elements. It will act also as a filter. So very often, this is kind of in perspective, like prefabricated elements, right, with hollow spaces, and those walls are porous, so water can go through, but not the dirt. So this could have such a filter. So this is a variation, in my opinion, a little bit worse than the one we saw before, especially for those 2 details in the front. It's another case. This is interesting because here we have insulation in the underground. So this is like a probably climatized basement, right? That means they have heating, air conditioned, and so on. So you need insulation, right? Also, the thermal loss underground is not so heavy. This is why the insulation is thinner than the upper floors. But yeah, this can be the case. They have even in the ground, but it is quite interesting. In the rest, it works more or less. So you have a variation on how to deal with the landscape, which is also okay. You may have this kind of a barrier between the planting, the flowers, and then the gravel. This is something we'll see very often. So you have a nice connection. The gravel will hide at this certain point, which is always difficult. We have another difficult point in terms of design, which is the waterproof. Waterproof is always ugly. So the waterproof ending point, right? If you have the wall, right, you have the waterproof layer and then the gravel, right? If you're not very careful, this is an open point, so the water can go in. So sometimes we put kind of clip, something which covers, and this should be enough, right? Sometimes it is hidden under, so sometimes you will see it hidden. I'm changing the colors unwillingly, but okay. There's the gravel. Can be hidden under, but still you have this kind of danger of the water filtering inside, right? You may have it in view, but then you have to be very careful how this will show. And again, we have no tripper. So there's always some kind of danger of the water filtering in this point, which is also a difficulty, right? And the rest, there's no variation, right? So it's interesting thing. We will see most of the details of the book, but the point is not memorizing them. It is for you to see that within the principles we saw in the first detail, you may have plenty of choices and you may work out yours, right? I'm just pointing out what I see of strong and weak points on each, and then you may decide. But obviously this area, which is what we all see, and the one which should be damaged, as the question 3 we saw before, we have to be extremely careful if we want our building to really, really stand over time, right? We have one more example, and this is quite common. You have the brick veneer on the outside, right? You see the waterproofing layers always exist there. We consider probably the insulation is waterproof, so it doesn't have problems with water. That's interesting. I don't know how they will do it, but okay. System to have a continuity of insulation, which is okay. That means that insulation is really strong against the pressure. For the rest, there is almost no variation. Only, again, I will be a bit critical of this detail, because if we have the concrete, right, and the brick, let's say it's red brick, right, the one which is very popular, right? Actually, we will have a mortar, right, in between. So this is porous material. If it rains, the water will slide and will move around, will come here, and eventually will go through. So I don't think this is a good detail. What we do very often, and you will see very often in projects, is to have, let's use the same colors for the sake of consistency. In the first brick, and remember, we cannot go out very much. This should be maximum 1/3 of the brick, right? Otherwise it might stumble. Is putting some metallic element, some kind of angle, right? Which actually may help supporting, right? This will be fixed to the concrete. This can also hold the waterproof, let's put the waterproof here, the waterproof layer, right, under or over. So the water now will naturally slide, and we'll have this area, which is the weak point, very protected. And actually you will have a nice view, right, a very clear ending point of this wall with this kind of metal element, which is hiding a dirty joint, which in this case is always on the view, right? You will see it ugly and dirty joint on site. I see some people leaving the class now. It is 15 minutes before the time. If you leave earlier, because I had questions about attendance online, if you leave earlier, we have your record of your leaving. So you will have this attendance taken off, right? Leaving early is the same as arriving late. If you had a kind of network problem, which may happen, you need to have the screenshot and the, right. So if you have that problem, just take the screenshot and come back again. And then we will see you return immediately, and then you will have no problems. But we have people who log in and leave after 5 minutes and never return again. You have people that leave like 10, 20, 30 minutes before the class end, right? I'm not speaking of this case, but I have to remind it. Again, careful with those things. And you see, this is a great book, and they are good architects, but still there are things they publish, I think could be improved, and we should be more careful, right? And I gave the reasons why, the possibilities to make it better, in my opinion. So let's go to the process. This is part of the slideshow we didn't see. This is a normal construction site. The first thing we do is to draw the excavation line. This is why we need very clear plans, very clear drawings in which you can find the references. We see the dimensions. We have the This is like a very precisely measured points, and we use the measuring tape and see the thickness of the line. This is like a 10 centimeters thick line, and this is a excavation machine doing there. So in this case, the millimeter dimensioning is totally meaningless. So once we excavate, you can see there's no precision there. If you're familiar, you can see the difference between layers, right? So this is like a terrible land you cannot use. This is the plantation one. This is quite okay, and this is the best part. So actually, it's what we call the quaternary geological times. This is tertiary, so it's like quite a few million years old. And this is the one which is proper for the foundation, right? You see all pipes, all remaining from all constructions, and those strings are the structural axis, right? And then we have to draw again the real foundations. Then if the excavation goes for more than a few days, it is a good idea to protect this plastic in this kind of a sand. This is a very good quality sand. This is Madrid. So if it rains, it will not decompose, or if it has strong sunshine, it will keep the humidity. Humidity makes the land more stable and more in its natural state. And this is next to a street. And in this case, we have the street, right? We have 4 meters, right? And then the excavation. So if something happens, probably the street will not be affected. If we were excavating next to the street, we would not follow this system, because if something happens, you destroy the street. And this is very embarrassing, dangerous, and expensive problem. This is one excavation to make a retention wall. You see the temporary retention is important. Always you have safe space for people to work. And then this is the bottom of the retention wall. This is the sand excavated and make it flat to have the concrete on it, right? This is a thin layer. It's like a thin 10 centimeters concrete layer, right? And just to have a flat surface over which to put the reinforcement of the foundation and the wall, right? This is the foundation already with the concrete. You see that we have already those rebars for the wall waiting, right? We call it, I don't know the English term, but it's kind of waiting rebars to overlap with the continuation. And then this is the point, right? When it is almost ready to pour, so you have the wall rebars, you have the plastic spacers, so the rebars do not touch the borders, a flexible joint with the neighbors, and then the form and the overlap. You see clearly, this overlap will depend on the diameter of the rebars, right? And then finally, you have to waterproof at least to that roof level. And this is the difficult point, right? What we do with this kind of a border, but this is a garden wall, so it's not very critical. And see how we need plenty of space to work under the wall, right? In this case, it was easy. We cannot always have this space for working. You see here that kind of porous pipe with a drainage, which will be connected later to this kind of a drainage wall later. You see, this is a different kind of a drainage layer. And see the gravel, just to make sure the water does not clog in and goes to the pipe. And you don't clog it with the sand, right? And this is important, I put clean sand, because sand for fields, you have to buy clean one, not contaminated. And very often the builders will save money and use all the debris, all the rubbish of the construction and put it here. That's terrible. This is polluting, this is dangerous, it will reduce the stability of the floor. It's forbidden. Don't do that if you're in a construction company. Even if your boss wants to save money, if you know it and you share that kind of action, even if you're following orders, you're part of the crime, right? You're guilty in most of the world. So don't do it. And if you're the architect, make sure whoever is in charge of the control, they are using good quality sand, right? Fillings. You can crush concrete, you can crush stones, you can buy sand, and we have, remember, we have the sand crisis, but you cannot use planting ground, planting only for the top floors, right? The final layers. So careful with this. This is a case I didn't annotate, but when you have a neighbor, right, this is a bit more dangerous, as in the street we saw before. If we excavate all at once, this wall may fall. So what we do is to excavate by bits, right? And then very fast prepare the rebars and for the concrete. You can see the gravel and the plastic before the concrete. So because this will be the basement border. So we have the ground. Over the ground, we'll put gravel, right? And then some plastic, and then the concrete will be on top of this, right? So this is what we saw before. This prevents the water to go up, right? It's preparation. You see how we paint the borders. Everything's very rough in the basements. So once you have these walls, that part is retained, you can excavate the rest, and then there's less danger. It is not always possible. You see, this kind of sand is very good quality, very solid, very dense, and it works okay. And it's okay for small basements, right? In larger, deeper basements, you have to be more careful. So once those walls are done, and you see that it is almost 1-to-1, so it has stability by itself, then you do the rest. And in this case, all this kind of a waterproof, this kind of layers, right? So with gravel, it's impossible because we don't have space. So on one side we can do it, and the other side it's impossible. So in this case, we will have to waterproof on the inside, or we have to resort to other strategies, right? Because we cannot work. We can put something in between, but in this case, we chose just to put the concrete against the wall and as fast as possible to avoid the danger of this falling. But if you have support at a reasonable distance, which is usually this width is more or less the height, right? Width is more or less the height. The stability, and then for this kind of quality of ground could be okay. This is an interesting case only when we have just a continuity of insulation, the connection with the rebar, with the steel, and this is perfect hinge slab. Usually one of 10 millimeters or even 8 millimeters every 80 centimeters or so, usually is okay. You don't need to put too many, but then the engineers will calculate that it will depend on the total weight in this area, right? You have some variations here, we will not comment. We have, again, another variation, we will not comment either because we have 8 minutes left. We're almost done, right? So this is interesting because having an in-between element is also interesting strategy, right? And then the water will slide, the need of that repair is not so urgent. This is one example of earth membrane. You see the gravel in the border and the ending of the waterproof just in that point, right? It's already commented. How can you have this border? This is little part of concrete. You see here, very tiny. And then you have the lamb earth, very sensitive against water. So you need to have always this kind of separation to avoid the water to erode that element. This is very minimalistic, but it shows you how we all fight with this very point, right? Okay, so at home, this is not the assignment, but I suggest you copy by hand and you review all the points we said. So you review it, you refresh your memory, and you interiorize it. So when you design yourself, you don't need to think about this. This will come automatically or naturally. So to end this part, I added a chapter on deep basements. This part was added in materials maybe 2 years ago. So probably if you did 2 years ago, you see it already. But I put up a few more examples. So this is we have to go deep and we don't have the space to work because, okay, I have to remind, this is the excavation line, right? This line here. So it's the space you need for people to work safely, as we said before, right? If you don't have this space, you cannot do all those things. This is the case we are studying here. So this is the project we saw before, I think, in the structures. You see the aerial photo and see the border of the plot. This is very irregular, and we have a lot of old buildings which are neighboring us, right? So in this case, excavation is critical. Before doing the excavation, we took photos of all neighboring buildings, and we went to the official site to have it recorded, because when you start excavating, all neighbors will claim all their cracks are because of your excavation. So you have the record of how they were before you excavated, they cannot complain. And you will see if you really damage, because it may happen, this is a real risk, you will have a record of how much more damage you produced. And that will help a lot with the insurance companies and in court. Important thing, right? This is the section we saw. So the question is how we do these walls, and also those walls with only one basement, right? So in this case, we use micropiles machine. You see the machine is very small. It is very thin. It's like about 15 centimeters, right? Drills. And they are very delicate, so they are not so aggressive with machines. So that will vibrate less in the neighbors. And also, since the piles are smaller, you will lose less space in your building, because the thicker the piles are, the thicker will be the basement wall, and the more space you will lose in those basements, right? So these are the details. This is the ground, right? This is kind of a long beam. So when you put the piles, you will always put kind of concrete beam tying them, and then the structure will be over this, right? This is what this element is telling. So in this side, you have at least 3 piles per column. On this side, you see only 1, perfectly in the axis, as much as you can. And this is the tail of the pile having some rebars welded. So when we put the concrete, it will be well tied. This is studied by the engineers, and they make the calculations, and it has to work, right? In this case, it was 12 centimeters, the micro piles, right? So when you have only one basement, you put the micro pile, then you put the beam, and before you start excavating, you put the tensor and you fix it. You drill it and you fix it to the land. Then you excavate, right? You excavate. And when you reach some level, you put another tensor so the wall will not fall down, right? So this is after the excavation, right? You put those tensors. If you have more, you have to put tensor as soon as you go down, you put more. So this element is stable. And see here how it's about 1/3 under and 2/3 more or less up. This is all calculated, right? Just to have enough support. Then as you start building basements, this element takes all the tension, so you can start releasing all those tensors, right, as you go up until you reach the top, and then the structure is self-supporting, right? It's working. This is the result. You see all the intermediate steps, and then as we go up, those disappear. When we go to the real piles, 3 minutes. Real piles are about 30 centimeters, right? They're much bigger, 30, 40, 50 centimeters. That means we need more space. We need some margin to drill. So we are losing some space to the border. Then we have some space to put all those beams on top of those piles, right? This is a section. So we need much more space. And those machines are very aggressive. So we do when we have plenty of space and very big constructions. This is an example of those piles. This is about 40 centimeters, right? And you see here the light. It is very hard to be precise. So there's a lot of area. You may lose between 70 to 100 centimeters in those walls. See the border beam, right? It ties everything. See those elements which you avoid to put those drill tensors. They're very expensive and very hard. So whenever you put compression elements, as you see in the corners, but the principle is the same. You see here already isolated footings going up, the preparation for the ground, and then the first ground put there. And then I put this because it's interesting. It is kind of, give me 1 more minute. It is, you see the beams, the columns are stopped in the level of the lower part of the slab, right? So this is the waiting rebars for the following floor for the overlapping. So you put a full space, and this is for waffle slab. It's very easy, very fast to make, very light, lost form. Well, you will recover later. And you have the space, you can see the space for the capitals of the columns, right? For that. And this has probably 30 centimeters, not more, total thickness. Here people are working on the connections. See how we have, let's go back. We have no columns on the border, so the slab will have to be supported by this wall. But see how the span is smaller. So in some cases, we could do this even in cantilever in the last part, right? So we could go in cantilever and do not touch the wall. In this case, they just reduce the slab to have less load, and they use this kind of steel connection as we saw before. That's what they are doing. there's some element to avoid the water coming in. You see there's the humidity there, but you see the tensors, they will disappear as they make the basement. But it's not easy to see. These are the steel rebars drilled. And in this case, they're put in every 1.5 meters. That means the load is very small, right? This is drilled, put the steel, and then when we put the concrete, so you have the pile, the steel, and the concrete poured, and will be supported by those rods, right? This is why this span is a bit smaller, so the load is not so big. This is what we saw before in the detail of the basement, right? This kind of connection every field. And we are 1 minute over the time. So I brought this of the capital because we can see this kind of zigzag is this kind of shear reinforcement. And that happens again as soon as we have less concrete, we have to repeat again, right? This is vertical bars. And in this case, they did in this way. Not so happy with these openings. You have to be always careful about them. And then in this case, you cannot make waterproofing, so the water will go in. This is why you put elements which will collect this water, right, and ventilate, so it will evaporate. We assume the water will go through, right? Sometimes you can have a waterproofing from the inside, right? Or you could put something in the concrete or put some kind of layer there. There's not many more solutions. In the SK feature hall, they have this kind of wall, and this is this layer of collecting the water that you can see from the front. It can be ventilated, accessible for maintenance. And then we put some sheet on the bottom to avoid the water coming in. Right? So when we can put the waterproofing. And that's enough. Again, apologies for these 2 extra minutes. Please, if you have any more questions, write them in the sheet. You can complain, we went very fast. But again, I hope, I will see the recording later. Tomorrow will be a bit more relaxed. Well, not relaxed, we have no time to relax. But we'll try to go more in depth into more details for the part over the ground, right? For the facade. And then next week we will see curtain walls, windows, and a bit more delicate things. So please write your questions or comments, upload before noon, please, and have a nice day. See you tomorrow at this time. Goodbye.